as an episode of this host after in this building series. So let's start off here. In the last episode we made arithmetic logic unit 1-bit full adder and in so we'll be working on 8-bit adder and maybe even the full 32-bit adder. This is just a series of 8-bit. It's actually relatively easy to do, and I'm sorry if there's any construction on this will happen here. Anyways, go ahead. Start with this. So this circuit is actually going to be derived based off of old full adder, the 1-bit full adder, which, as you can see, as simple, A is on, 1, if B is on, 0, and if carry flag is on, it also becomes 2. Now that's pretty much fine. There is actually a way that we can go ahead and do this to make it a little bit easier to follow. We could just use a gate of 4-bit add, 4-bit and then we could also do something like that. But I think that this is actually fine. And to be fair, the 4-bit add probably wouldn't work. Just thinking about that out now. Either way, we're going to be using this, which comes out to be these modules, right? And then we're going to go ahead here. That's pretty much what we're start. We're going to take it and make copies of it. We can bits. And actually go ahead together with that. 2, 4. So now we have bits here of our overall. Perfect. So then we're going to take input here. This is going to be in or carry flag in, because the carry flag can still be set regardless of the bit width that we're doing. So in this case, we're doing. So label to the north and half that. Now that we have in, go ahead and connect it here, and it counts as the input for our carry flag. Then we'll copy here, take F out, which is going to be a output of our module here, and north with the text. Now that we have this unit, connect it onto the end here. Since not everything is wired up, obviously we create this issue where it will error out. Now, what about the bits? So we're going to actually be taking in 2 inputs and an output. So we're going to use these 8 with, this 8 data bit with input output pins, and this is going to basically be the representation of a full bus of data, at least in this breakdown. So this, in fact, refers to the 8 bits inside of a byte, basically. So it's going to be a 1-byte adder. And the reason I'm doing it based on 1 byte is because in a lot of processor designs, for example, x86, you have various levels of registers. So you have EAX, which is the full 32 bits. Then you have what would be AX, which would be just the 16 bits. And then you would have AL and AH, which are the upper and lower 8 bits. This might need some further considerations, and we're not necessarily going to be implementing that. I might, but it's not necessary for this thing. So we're going to make this one A input, okay, a second one, which is going to be B. Furthermore, we want to obviously have voltage. And out here, which is going to be an output pin, and we're going to get R, put this on the east side and base. Now this is going to be Now, what we can do to combine or split inputs is using the splitter, which in this case is going to take A input, and then it's going to go ahead and split it out into the bits. And furthermore, we can also use it over here to unify them by all outputs and bring them out of the output register or the output pin. So what this pin does is that we're going, what the splitter does is that we're going to probably go ahead and hit west, wireless west, and just go drag it here and do. Now I'm going to go ahead and basically just set up for every single thing. It's pretty easy to do wire hookups. Just click, bring it over, okay? And that's the way that I'm doing it. Relatively nice, and pretty much here. A lot of it doesn't need to look nice, but I find it good to have circuit designs that you can really understand with some processing, and it shows an overall flow of it. So right now all errors because we don't have any inputs, and this looks pretty much fine for the result. So now we're going to go ahead and insert over here for the basically the entire input. So I'm actually going to make it facing right-handed, that way that go ahead, line up 0, A side of our adder, and then I'm just going to go ahead and so I want to face that I can go ahead with B, and then these here, every single blue means that it's not affiliated yet. But I believe that it's pretty easy. I just hold E or hit simulate and hit simulation in order to be able to have basic communication. Then we'll go ahead, goes down, and once more for here. There we go. So then I'm going to go ahead and B, bring B here, and create a splitter. This one that's going to be left-handed, that way. Sort of nice. Line, and this parallel, so 7th bit is going to go ahead and input here for B, and then I'm just going to go ahead and connect it for every one. I'm actually going to take a turn here before the wiring, that way we don't have any sort of crisscrossing build unless we can't do it. So just mouse accuracy is pretty nice design. And or you don't want them to tie together in the same line, because then it just and it actually will function correctly because basically either one is on, yeah. So then I have space here, and because there's no really good alternative, because if I cross into these lines, then I'll tie them together with one. So this looks pretty good, and if we go ahead and go to interaction tool over here, we turn on back in, we get one bit set. Right. So let's do some really basic math. Let's go ahead and let's take A, and then we're going to say, let's say 7 plus 10 is 17, right? So to do 7, it's going to be 1 plus 2 plus 3 plus 4 is 7. Then we're going to go ahead and do 10 over here, which is 8, 2 is 10. So now we're going to say 10 plus 7 is 15. So I'm going to go here, and 15 plus 1 is 17. And we know that the result is correct. So now that we have a 8-bit adder, we can go ahead and work with 16 and 32 bits. To really do it past this point is actually much simpler because the splitting is easier. We're not really going to be splitting that much. So we're going to go ahead and work here, give 16-bit adder, which we can go ahead and as 8-bit. One thing that I should mention, 8-bit is that really good. Not too bad. Size it, and we can output, carry out, and this one in. Then we're going to take A and B. There's go ahead, place them out the border, two gaps, two gaps. Now that's done. Yeah. This actually just determines which way it's facing. So I don't really, but and then we can send it. That's hard to do. There we go. It's on the line side. Yeah, that looks much better than it was before. I'm gonna take that 8-bit adder, throw it down here, do the same thing, connect them again, and you're gonna notice that pretty much it's gonna look a lot like that. So the data bits on its output and its north label in the south is gonna be out. Okay. Then we're gonna both south, and we're gonna go. Cool, we got that set up. Next thing that we have to do is splitter, and we're gonna do it differently now. Because what we can have is that we can have a 16-bit in and a fan out of 2. So what this is going to do is that out here, I can actually just take bits 0 through 7 on the top part, and then bits 8 through 15 on the bottom part, and I can use that in order to just look correct. So let's go west. I'll put here, and then I'll into a Bolton pin, and instead of 8, it's going to be 16. So the maximum bit width in this program is 32. So we have this as our output, and label location east that says results are. We're going to take our connection here, send it there. But now we have a output for our adder. Next thing, of course, we're going to take a 16-bit input, which is going to be A, and another input B, and pretty much it's going to be the same process with the splitter, but now we're just taking it. So here, then here, over here, and then boom, we have A. We're going to here, we're going to go ahead, splitter, drop it here, and then make base right-handed, so that even pattern up here. Then we're going to take here, bring them over, and then bring this across. And now we have a really nice circuit. I'm just going to select these and move them closer in order to make it a little bit more compact. Same stuff. Make it a little more compact. Now we can go ahead and test it with the traction tool. So, this is bottom bits. So I'm going to say we can go ahead and test another arbitrary case where we're going to want to do like, let's do 13 plus 54. So we're going to go ahead, 8, we're going to take 4 plus 8, 12, and then we'll go one more, and then we can go ahead and say 4, we're going to take 32 plus 16, 32 plus 8, then we need 54, difference there is 6, so we're going to 4 plus, so 4 plus 2 plus, so the way that you add binary is either 0 or 1, so this is going to be 1, and then 2, 4, 2 plus 4 is 6, then nothing here for the 8 spot, nothing here for the 16 spot, nothing here for the 32 spot. Right. 1, 2, 4, 8, 16, 32, 64, 1. Sorry, I have messed up. Bit order. There we go. So now it's going to be 1, so there's nothing in the 1 spot. Then 2 plus 4 is 6. 6 plus nothing inside of the 8 spot. So then we're going to go over 16 spot plus 6 is 22. 22 plus the next spot is 32. 22 plus 32 is 50. So then we're going to do 54 plus 16, which is going to end up becoming 67. So we're going to have 64 plus 1 plus 2. So 64 plus 3 is 7. So 67 our result. And this is just a very simple verification for math. Now, of course, we're going to go ahead and set the module up, nicer, in order to make our little so that we can go ahead and make a 32-bit adder, which is going to, follow basically the same thing. Hello. Sometimes they don't want to move, and something big must be happening, right? And it's just the news group. Cool. Nothing very interesting. So let me just check with. Actually, want them to be close enough. Okay. I just wanted to maintain consistency for what I've already built. Oh, actually, closer, and that looks fine. This is going to be our 16-bit adder, and then we can go ahead and another one for the 2-bit full add. So we're going to take the 2-bit full adder, it's going to be 8 bits. Together here, together, and we're going to go ahead and have pins. So, pins. Now it's going to be the full data bit width of 32. Big is going to be the output. West, east, with the label R. Then we're going to go ahead and take our splitter, and instead of the within of 16, it's going to be the within 2, not 23, 32. And there we go. We're going to go ahead and put it here, west. Then we're going to actually, oh, sorry. There we go. Now that we that's the bottom. So now we here. I'm gonna go ahead. Pull off further. Move them down. Doesn't really matter too much. Take one in for our 5, 4 in, and we're gonna go ahead and out and 2. And the reason that we're still gonna have the carry flag in and carry flag out as a single bit is because it's part of the CPU's flags register, which is gonna have all of the different flags. Or, 0 flag, it's gonna have all these like that. So CF in output, facing north, label on the south side, and it's going to be. So whatever the result of CF out is in our basic ALU unit is going to go ahead and compute as being that should be stored in. So taking a look at that. Okay, cool. And then we're going to take another here. It's going to be input. We're going to take it into the splitter now. Phase, right? Case. Right side? No, I'm going to have this left side right. This there. Pull it across. This one. Then we can go ahead. Label this A, obviously. This, copy it over. So, E, flip this to be 5. It doesn't work out. I can go that way. This come across. This pulling. There. Cool, now we have. And of course, this default. And now we have a full 32-bit adder that we can do math on, and as we can see out. So, one last thing, and this part of the video, I'm gonna go ahead. And this is gonna adder simple. This in and use it. I still will probably do components for the ALU, but this is gonna be I'm actually gonna put labels on these as being a 32A, and 8. That way we can have labels on each of these that show that they are labeled BA in it, and then Queen BA. And that makes it a lot easier to go ahead and look at in general. You can actually probably add the adder and label for 1BA. It should be a full adder, so 1BFA. 1BA. And that way we can sort of tell what components are without necessarily having to look too far. There we go. The project. And this is where we're going to leave off for now on our design of a CPU. So in the next video, I'm going to be doing some of the other modules and units that we're going to need for the arithmetic logic unit before finally doing the actual logic unit for basic add, among a bunch of binary operators. By the way, thank you guys for watching. Please like, comment, subscribe, and I'll see you guys in the video.